It's really my distinct pleasure to introduce our plenary speaker today, Professor David Donoho, who really does not need any introduction. He is the N.T. and Robert M. Bass Professor in the Humanities and Sciences, and also a Professor of Statistics at Stanford University. He's really one of the most renowned statisticians of his generation. He has made fundamental contributions to the theoretical and computational statistics, signal processing, and harmonic analysis. He's very well known for many contributions, such as the maximum entropy principle, robust statistical procedures. And personally, I got to know him in 2011 when he gave a plenary lecture on sparsity and compressed sensing, and he's been, of course, one of the pioneers of that area as well. He has received numerous awards for his work that could take me an entire lecture to mention, but just the most important: he's a MacArthur Fellow, John von Neumann Prize, Norbert Wiener Prize, Carl Gauss Prize, and he's also a fellow of the American Academy of Arts and Sciences, the National Academy of Sciences, and recently he became a member also of the American Philosophical Society. So we will proceed now with David's lecture. That will be about 45 minutes. And if you have questions, we are asking that you ask the questions at the end. You can go at the bottom right of Zoom and there will be a Q&A, and then our co-host Gita Coutinho will be moderating the questions. So without further ado, we're very honored to have you, David, and welcome.
Well, thank you for the kind introduction, and I want to thank the organizers for persevering and allowing us to have this kind of remote presence meeting. I'd also point out that if you can see on the slides that the talk materials are available at the link that's on the first slide, and then you'll see again on the last slide. There's a question and answer following, and of course there's another talk tomorrow. So I wanted to speak about COVID-19 testing. And there may be a certain amount of COVID-19 fatigue, so I feel I have to first explain why I'm doing this. I think the first thing that we've got to recognize is that what we've just been through, the lockdown that is now easing, is really no different than anything that humans have done when facing a pandemic for thousands of years. So this particular lithograph shows you a depiction of, what happened on a Passover thousands of years ago in Egypt. There's the angel of death. There's the family cowering inside, afraid to go out, so on and so forth. That's really no different than what we've just been through. And if we look even to the period of the Middle Ages, medieval times, we can see here a wood block that gives us a picture of someone who's gone out to market and is coming back in from exposure to the world around, and lo and behold, they're wearing a mask. Basically, what we've just been through has complete faithfulness to everything in the human experience to date. There's no high technology aspect, and science has not delivered any difference in that element. What it has delivered is testing, so that we do have information we did not have previously. You can see this fairly up-to-date chart, which presents for you the graph country by country of the total number of COVID-19 active virus tests per 1,000 people. And you can see here, for example, that the United States has been able to test over the entire course of this disease about 8% of the population, as has Italy. Denmark stands out at a much higher level, closer to 15%. So we know something about the disease because we're testing, and it's great that we're testing quite more than we were a month ago. And the more we test, the more we see that this whole problem is really far from over. You might imagine that because the news programs are losing interest in COVID as a theme for viewers, you might think this is all over, but actually we're seeing more cases globally than we've ever seen in a day. And if you now look at states that were traditionally unaffected, like Texas and Florida, you're seeing more cases than you've ever seen in a day. And moreover, because of the exponential growth of these things and the increase in the curves that you see, it might only be a few days before you start seeing New York style events in any of those cities and states. So this is not really over, so I feel it's okay for me to still be talking about it, although we're all suffering COVID fatigue. That's a stipulation that I'm going with. I want to call your attention to an initiative that's been taken by Paul Romer. He's a Nobel Prize winner in economics in 2018. He's been the chief economist of the World Bank. He's a professor at NYU. And for about 2 months, he's been, clanging the bell of, we have to have more testing. And the level of testing that he wants is way beyond what we've been able to deliver to date. So here's a quote from a Wikipedia article discussing his ideas. Paul Romer believes the US already has the technical capacity to scale up to 20 million tests per day, his estimate as to the number that will be necessary to fully remobilize the economy. This would cost maybe $100 billion, and it would be okay even if the test is relatively inaccurate, provided it's administered frequently enough. He wants 7% of the population tested every day. And he shows that, that will work. So every person would be tested roughly every 2 weeks, so twice a month. So compared to the plots that I showed you, this is 7% of the population every day versus in the US, we've been able to test 8% of the population in 4 months. So it is a dramatic scale up over what we've been able to do or what we envision being able to do absent Romer's campaigning. It's been a ritual to give thanks out of this COVID-19 to caregivers. And in New York and some other cities, people would bang pots and pans and play harmonicas and violins and things. It's every night at 7 p.m. But there hasn't really been thanks for the testing technology that we have, or even enough prominence to the fact that we actually have testing. So I thought I would just say thanks to the scientists and technologists who created the tests, the government agencies who rushed emergency authorizations that made the tests available during this crisis, and the many organizations manufacturing test kits. That's my thanks rather than banging pots and pans. Of course, my son is a doctor and faces COVID-19 risk. I certainly thank him. That's not my point, is that there's a relatively underappreciated group of people, and that we as technologists and scientists here should actually recognize that. So there's an underlying technology that I will describe, and there are scientists who've been working on disease testing and rapid scale up really for decades. And there've been actually a lot of citizen scientists who cross-applied their ideas from some other field trying to rapidly scale up testing. I want to say thanks to all of those people. And so this talk is really like a thank you bouquet to all the people who've developed testing technology, and talking about some very recent research by others, which is proposing how we could achieve further dramatic scale-ups, getting us in the direction of Paul Romer's request. So what I'm going to do is review some of the exploding COVID-19 testing literature that's appearing on medRxiv, tell you a little bit about how active virus COVID-19 tests are conducted, and then ideas coming out of our community which could expand testing dramatically. So an amazing thing that's taken place because of COVID-19 is that medRxiv has arrived. While math scientists and data scientists and physicists and so on have had archive for almost 30 years, the medical profession was never interested in that kind of rapid publication pre-refereeing, and they were always paywalled and everything was very, very tightly controlled. As it happens, medRxiv started last year by a collaboration of Cold Spring Harbor Labs and Yale and BMJ, and still one would not have expected it to take off absent the kind of incredible global crisis, which was simultaneously a health crisis and a global economic crisis. And because of that, somehow everyone suddenly has permission to share their work, and the paywalls have come down and so on and so forth. So one thing we're seeing out of this whole development is the flowering of medRxiv. And it's quite interesting that as the case counts have been increasing, so have the daily preprint counts here. So we're really realizing thousands and thousands of medical research efforts, all focused around what to do about this crisis. And there's been a lot of rhetoric that because of the development of medRxiv, the world has changed. So you can go and see all sorts of very interesting conceptual pieces where people are writing essays about how the world is a different place because coronavirus is making us work together and share knowledge and so on and so forth. And I encourage you to follow up with some of those things. What I'm doing in today's talk is reviewing some literature that's principally appeared during the crisis on medRxiv. And just to show you how global and international the effort is, I've made a little map here which pinpointed some of the papers that were beneficial to me, many of which I'll be able to cite or at least very quickly gloss over. And so you can see there's really been a global effort using medRxiv to share information specifically on the theme that we're going to discuss today. You can see there's quite a few papers that are just on this one theme have come about in only a few months. And of course, there are many other things being discussed on medRxiv, and it's really a global collaboration. This is quite unprecedented in medical science, and a great deal of progress is being made. Thank you, medRxiv. So there are claims emerging from the medRxiv explosion saying, you know what? You can get a dramatic scale up in the amount of disease state evaluation by simply using your test scanners and your test kits differently. So there's a paper by Claudio Verdun and co-authors who are cited at the University of TU Munich and University of Vienna. And they make claims as I've highlighted here. All 1.47 million inhabitants of Munich could be tested using only 141,000 test kits under some conditions. Or we could test everyone in Rio using, again, something like 1/10 as many test kits. And of course, there's conditions on these. And all of us as mathematical scientists, data scientists would want to drill into it. I'm just showing you an example of a paper that's out there on medRXiv and is part of the wave of publication that I'm featuring for you. Another thing about the claims is that these are additive or supplemental to anything else that's done scaling up. So, if you have more RT-qPCR machines, if you have more reagents, so on and so on, this still works on top of that. Another thing is that in Romer's analysis, he's made a lot of contributions, but he's not assuming that the existing technology can deliver what he wants. So he's not assuming the use of any of this technology. He's assuming that some miracle technology that's not currently on the market will be seeded by massive federal investments in research. Whereas what I'm talking about here is something that uses existing installed base equipment, existing equipment that doctors are routinely invoking and everyone knows how to use. There are caveats, and we'll describe what those are. So as some examples of papers that have hit medRXiv over this period, I just list a sampling here. And I know if we were seeing this live, the print would be too small, but maybe you can see the print. I hope maybe you can at least see the titles. So just, a series of papers, and they're listed out in reading order, roughly by the order in which they were posted on medRXiv. So you can see, a paper from the Technion, then one from Nebraska, from a university in Spain, in Texas, so on and so forth. And the one that I just quoted on the previous slide is there in the lower right. So there's a series of papers that are out there on medRXiv, and I'm just scratching the surface. I mean, as I showed you on that map, there are many, many papers that one could look into, and which I did look into, and was just really inspired by all the research that's going on. And so you can view this as a research front that has established itself in a relatively short period of time. And some of these papers refer to each other. So it is a kind of dialogue or conversation going on globally as we sit in lockdown, but we discuss how to get out of lockdown by supercharging or turbocharging existing testing technology. Now, data scientists envisioned this day a long time ago. So here's a paper from Annals of Math Stat, 1943. That was during World War II, and the author is cryptically from Washington, D.C. Who knows what that means? And the author offers this research contribution, which is, you don't have to test one-on-one. You can create pools, and then you can do things adaptively based on whether there's any bad blood in a pool, and develop, math analysis based on binomial distribution properties and, things that are quite elementary today. But that is a method that's been out there for now 80 years, and it's been used in those 80 years, and it's being used today as a prevalence determination tool. So if you want to know how many people in a county have the disease, you just pool all their samples together, and you see if thereby any of the samples have the disease. And he talked about a scheme that would actually allow you to narrow it down and figure out literally who has the disease, not only just is there one in a group, and that would be done by a sequential process of putting people into groups, and if certain groups go positive, then you drill down and do finer testing. Came up with the idea that depending on the prevalence rate, you should work with different groups. So at a prevalence of, maybe 7% in the population, you would test 5 people at a time. And if a test came back positive, then you test every individual. By doing that, you could save 50% on the amount of testing cost. So the total number of test kits that would have to be used up would be half as much for the given thing. So this is, a traditional idea. It's been out there for a while. And you can see how at low prevalence, this kind of procedure gives you many fewer tests per 100 people testing. So to test 100 people, you can, at a prevalence rate of 1%, you only need to really make 1/5 as many determinations of whether there's infection in the blood. Okay, that's classical. And then, move ahead 50 years during the HIV health crisis. In the early days that there was an antibody test, there was a tremendous clamor of people wanted those antibody tests, but there weren't enough tests to go around. And so in order to deal with that, as this article by Marcello Pagano in the Journal of the American Statistical Association showed in the day, they proposed a method based on a kind of recursive partitioning, test 15 people at once, and then depending on whether that comes back positive, divide into subsamples and so on. And they showed that if you did this, the number of tests that you would need to do compared to the naive number 15 would be dramatically smaller, but that would depend on the prevalence. So if the prevalence is low, you can do way, way better than doing 15 tests. And even if the prevalence is 5 or 10%, you can do substantially better. So what came out of Dorfman 1943 and everything that followed is if the prevalence is low, you can evaluate the disease status of N people with fewer than N test kits. And the prevalence range is favorable because really we're interested in testing a large fraction of the population rather than just people showing symptoms. And I don't think anyone believes that the disease is going to have active virus at rates higher than about 10% of the population. So Romer did simulations in which he sees it peaking at about 8% of the population in any one wave, and then in between it might decline even below 1%. Now, many algorithms were developed after Dorfman. There's a lot of literature in the mathematical sciences. This includes statistics and in many SIAM publications. In order to really explain to you what's going on here, I do have to review some of the underlying science of COVID testing. And so I'm going to give you a little bit of information about how the actual reverse transcriptase quantitative polymerase chain reaction devices work. So RT-qPCR. This is the gold standard for COVID-19 testing. Other approaches may be developed or may be proposed. This one has been available since mid-January, and the reference standard was created by Charité Hospital in Berlin, and they have been the go-to group for all the important virus tests since SARS. So whether we're talking about, H1N1, HKU1, any of the things, MERS, these things, the Charité team is just very, very good, very, very quick and precise. It was vetted by the CDC and then was given an emergency use authorization by the US Food and Drug Administration. And today, the major players in laboratory blood testing and testing of swabs, Quest, LabCorp, these are national scale organizations. They're doing hundreds of thousands of tests out of this basic standard. As I said, it is the gold standard and it runs on hardware that's widely available around the world. The thing that makes it a gold standard is that it can detect as little as 10 virus particles in a sample, and it detects a specific RNA sequence of between 100 and 200 nucleotides. So there's very, very little possibility of it being fooled about the identity of the virus that it's talking about. There are some details of it which are relevant for your understanding of the possibility of doing pooling. So let me just say a little bit about polymerase chain reaction. This is the idea of PCR is that you can create essentially a desired sequence that you want to find in some sample, and you want to amplify its presence. So if you find it, you're going to amplify it. And the way this is done is by cycles of warming and then cooling the underlying DNA that is being amplified. So that you first of all bring almost to boiling point, like 96 degrees, and at that point, any DNA is going to denature into separate strands. And then you're going to cool it, and you're going to have a primer in there which is going to attach if it sees that particular sequence. And then there's going to be some other, nucleotide supplies. And then you're going to warm it up slightly. And this is called a thermocycle. And each time you do one of these cycles, what you will have done is split apart DNA into two and then build a second strand on top of each of those two guys that was liberated. And you will thereby have doubled that piece of DNA. And then if you do this again, you will double again and again and again. And so if you repeat this for 20 or 30 times, you're going to tremendously amplify even a small number of original DNA sequences. And so through this, you can detect, this is the mechanism by which you can detect very small numbers of DNA. Now, it's not enough just to amplify, you have to know that you've amplified. And in order to do that, there has to be some way to read out what's accomplished. You're producing this soup by cooking. How do you know that in the soup you either have or don't have this desired target that's being amplified? Well, you do that by fluorescence, and you attach fluorescent devices onto this probe that is looking for specific DNA. And then at the key moment, you liberate the fluorophores so that they fluoresce and you get a readout. And in the process of doing that, your readout is telling you how many of the target amplicons you actually have in the sample, because it's going to be directly proportional to the fluorescence. What makes this work is actually, a fascinating little story that at Yellowstone National Park in Mushroom Springs, there's a hot spring and there's a bacterium there, Deinococcus thermus, T. aquaticus, that can live almost in boiling water. And out of this, there's a polymerase, tacpol, that is the thing that can go in this very hot soup and liberate the fluorophores so you can read out if you got any of this stuff. So there's all kinds of technology that had to be invented for this. And oh, by the way, since we're dealing with a virus, it's not based on DNA, so we have to do reverse transcription to create complementary DNA on which we can then PCR. So there's a lot of technology, but it's highly relevant to whether we can pool, so I'm going to explain that. And then there are these commercial devices that are used for running tests. And usually these are run, test one swab at a time or one blood sample at a time and so on. One element is the manufacturer's calibration that they do on the testing devices. And this is something provided by a manufacturer, Thermo Fisher, on one of their devices. And what you see here is a fluorescence curve versus the thermocycles that you've done. So on this sample, after 16 thermocycles, there's a little bit of fluorescence, and then you see rising fluorescence as you go through the cycles. A completely different sample with 1/10 the amount of virus gives this curve. A further diminution by a factor of 10 gives that curve, and then this and this. And so you can see that you can weaken the sample's contents by a factor of 1,000,000, and the cost is just you have to wait more thermocycles in order to get the readout. And so essentially it's possible to detect very sensitively small amounts of virus. Okay, so that's the background, and you need that background to really understand what's been said in the medRxiv evidence that I've mentioned to you. So here we have one of the first papers, and it's since appeared in a journal article. It's from University of Nebraska, and I'll give a shout out to the fact that Chris Bilder, who's a statistician at University of Nebraska, is an author on this. Being one of the first papers on medRxiv and first papers in the journal is definitely because Chris has built his career on pooling of, in every way, so many articles, so many projects that he's worked on. So he is obviously connected and can make things happen quickly, and that's just what he's done here. So of course, all the other team members contributed, but he was definitely ready to go. Here, what you see is that they are very conservative. They say, we pooled people in pools of 5, which is an idea you would have had if you had just read the original paper of Dorfman, 1943, and we got excellent results. And we're able to essentially double the number of patients we can serve with the same number of test kits. And as part of this, just to verify that this works, they show that the number of thermocycles before detection is a bit later when you pool than when you don't pool. Remember, they're pooling like 4 or 5 samples here. So instead of seeing the fluorescence cross the given threshold that the FDA established for detection, you don't get it at the number of thermocycles originally. You get it a little bit later because you've diluted one sample with COVID with a bunch of samples that don't have COVID. And so it takes a few more amplification cycles in order to see it. Okay. Then a basic science paper produced by a team from the Rambam Hospital in Haifa, Israel, and Technion talks about how far can we push this whole technology. And they kind of say everything right here in the summary. A single positive sample can be detected in pools of up to 32 using the standard COVID-19 RT-qPCR test. So this is very important. The standard COVID-19 test, I told you that the FDA has given emergency use authorization for one specific way of doing it. So maybe, you know, as intellectuals, we could think of other things we would do with this equipment, but what they're saying is you can pool up to 32 people and still detect that there's only one sick person if you use exactly the FDA EUA procedure. So they're exactly delivering what is, you know, relevant. It's maybe basic science could have gone farther. So as part of this, they give these curves, which again are like the things that manufacturers have shown. So they show here, if we just have a positive sample all on its own, well, the COVID fluorescence emerges at about cycle 28. Whereas if we start diluting things, then we emerge a bit later. And so you might not see, like if you dilute with 63 negative things, you've got, you know, 1/64th the virus. So it takes several extra doublings in order for the fluorescence to emerge. Another thing that's nice is they show you all the positive cases that happen at the Technion Rambam Hospital in the week early March before the work was published, and they show you all the negative cases down here. So cases that don't have COVID, eventually you start to see a pseudo signal, which is why you have to cut off before you get to 40 cycles, and that's part of the FDA standard. So you need to see emergence prior to 40, and they're saying, yes, we can do this. Okay, so those are some of the things that are out there in medRXiv, and it goes on, and you know, there's papers, you know, all kinds of interesting things going on, which I really can't talk about. But I'll just try to give a little bit of information for data scientists, just to indicate some of the more interesting recent work. And even here, there's more than I can possibly discuss. So I just, you know, the fact that I'm featuring these papers and not some others, I just have limited time in my talk, and you know, I had probably a varied audience. So if I leave out a paper, you know, that I could have discussed, I'm very sorry, you know, but I have limitations of time. Okay, so if I were trying to think about the problem of pooling and using these machines and so on and so forth, maybe as a data scientist, I might describe the problem this way. We have capital N individuals overall, like maybe N could be hundreds or thousands in some batch. And each one of them has a given amount of viral load. Let's say, this is hypothetical, I don't know the viral load, but existentially there is a viral load of all of them. And the viral load could include 0, like maybe they're not sick and they have none, or maybe they're very sick and they have a lot. Then what we imagine doing is having capital T test pools, each of them of size K. Namely, a pool is, I'm going to designate K out of these N individuals to participate, and their swab or blood, as the case may be, is going to be pooled together in one amalgamation that is then going to be tested. And then I'm going to make a measurement which under the FDA emergency use authorization is indicated here. I'm simply going to get a binary indicator of, is the fluorescence at thermocycle 39 bigger than 300? That's what the FDA says I need to know. Okay, it's binary. So I get the sequence of binary results. And let's say I want to use generalized linear models to interpret these things. So this is Bernoulli with some probability model that's a function of a linear predictor. In this case, the linear predictor is just a linear combination or affine combination of the underlying viral loads. And as the viral, the amount of viral load in the original sample goes up, the probability of seeing fluorescence at cycle 39 goes up. And so there's this underlying linear predictor in a generalized linear model. If we gather all the linear predictors together in a vector, then there's an underlying linear system that relates those predictions to the viral loads of the individual, and there's a matrix M, which you could call the pooling or measurement matrix, which is describing the relationship between the virus in patients and the virus that's in the test kits being evaluated. So we have this matrix. We can view it, a statistician might call it a design matrix, and it's just binary and some descriptors that could be interesting, could be the row weight, the column weight, and any of the other standard things that we think of in looking at these. And when we're trying to scale up and have fewer tests than individuals, then in essence, we're talking about solving an underdetermined system of equations somehow. Now, of course, the fundamental theorem of linear algebra is an obstacle to that, but the key point is that the disease has a low prevalence, which means that the number of non-zeros in the viral load vector is small. And so most of the people are not sick at any one time, just a small fraction of them. So that's what drives, a lot of work in the math sciences over the last 20 years. And we have combinatorial group testing, which has always been explicitly about this. We have sparse recovery and compressed sensing, which are subfields that have developed over the last 10, 15 years. And they're all exactly trying to do this in some way, according to some rules and using some techniques and ideas. Okay, with that as background, I can go farther into the medRXiv papers and say a little bit more about things that they brought to bear. So here's a paper from a team principally at Ben Gurion University in Beersheba, Israel, and at the Soroka Medical Center there. And they're talking about, again, the idea of we want to detect asymptomatic carriers. We want to be screening at the population level where most people don't have the disease. And they describe, the details of, you have a large batch of people, and then you segment 384 people into 48 pools according to a combinatorial design. And then there's a decoding procedure that comes out and labels for you in this eye candy version, that there's 4 people and notionally in the 384 and so on. So they're at least targeting 1% prevalence in this, and they're showing, and at least conceptually, that they're getting, good results in simulations and on, some amount of real data that was available to them at the time. They show the success of their procedure. And they're using combinatorial group testing ideas, which you can read about, for example, in these books from World Scientific that many people may have seen or known about. And definitely, the authors knew this day would come, and they've definitely been anticipating the development of tools and technology, and it's great for applied math that we have colleagues who've done things like this over the years to prepare for this day. And it's great to see that the world is able to use these ideas. So again, thank you, but not necessarily this time to the nurses, but how about the researchers who've been working for decades on these themes. Another group that I think is quite interesting is a team that's principally, I think, in IIT Mumbai and in the tech industry in Bangalore, but also with some presence in the United States, as you can see here. And what's really remarkable in their approach is that they produced an iPhone app, or maybe it's an Android app, that kind of guides you through this. So it shows you, you give it some basic information, and then it tells you what pools to use. And then you set up those pools, and then you input the binaries that come out, and then it tells you who's sick. So they do everything. They design the experiment for you on this app, and they do the inference. So that, like, they're essentially removing all barriers to doing this. And I think, you know, this is an example of how the world is changing. People, to make their work relevant, is making it utterly painless to actually do, if you're willing, you know, if you're willing to do it at all, there, you have no excuse that you have to hire a PhD or anything. They've done it all, and you know, they have the same type of eye candy. The nice thing here is, you know, they indicate how many thermocycles before fluorescence. And so you have a plus or minus, depends whether you reached fluorescence by the indicated number of thermocycles. So here not, here not, but in these two, yes. So there's someone in those pools. Some inference needs to be made of who's sick. And they constructed very specific matrices and did, you know, tests on various data that were available to them. And they gave some examples of using their approach over Dorfman. Now, the approach that they proposed was inspired by ideas in sparse recovery and compressed sensing. And it's inherent in those ideas that you don't do something sequential. You do one, you know, there's just one round of testing. You don't adapt after you see the results in order to decide who to test next. And there's some advantage to doing it that way, so that you can have fewer total tests if you have like more clever algorithms that can do everything in one round non-adaptively. There's also less delay for patients. And they document all of this and describe, you know, the particular designs and examples that they have. And, you know, just so you can see that, you know, if you look in their references, which of course they refer to some of the other articles that I mentioned, but they also refer to Dorfman's paper, some other papers by members of our community, like Rob Tibshirani for the Lasso paper and so on. So you can see that our community has had at least, you know, a shout out of as having a positive effect. So here's some summarizing points, and then I have some aftermath points depending on the time. So math and stat have been interested in pandemics for a long time, and not only the testing aspect that I've spoken here about, but the idea of forecasting the spread of epidemics using various kinds of differential equation models and so on. That's more than 100 years old. Economists are seeing the COVID-19 lockdown as a tremendous economic catastrophe and are proposing massive, massive expenditures as a way out of it. The nice thing about the COVID-19 situation is that its actual prevalence is compatible with the pooling ideas that people in the math sciences have been considering really for decades. And pooling, because of the way RT-qPCR works, pooling is really compatible with the use of RT-qPCR. And as you can see, there's even apps that will show you how to pool and will do the inference for you. So pooling really would allow us to scale up at actually not such a great cost. Maybe the 100 billion might not actually be needed. As a postscript matter, I want to point out that there's been just in the last week some quite interesting news. So first of all, about a week ago, or exactly a week ago, the FDA legalized everything I'm talking about. Namely, there's now an emergency use authorization that allows you to do what they call sample pooling or multiplexing on asymptomatic people, which is exactly everything we've been talking about. So the FDA says it's okay to do that. And you can read, starting in the third paragraph, they're saying that. I'm not going to bore you with all those details, but it's now legal. So this medRXiv is not talking about stuff that's forbidden by law in some way. Secondly, at around the same time, Paul Romer, the economist who has been agitating for much higher levels of testing, wrote this op-ed piece together with two politicians, a Democrat and a Republican, proposing a series of massive prizes to expand testing. And essentially we're at 3 million tests per week, and they want to get to 20 something million per day. So they want people to give them ideas, and so there's money for this. Technology that's been developed by mathematicians is certainly relevant and certainly a part of the picture. I do want to point out that I've given a lot of prominence here to Paul Romer. I don't want it to be that like I'm his fanboy and that he can do no wrong. It's useful to understand that he's doing what he can in the way that he thinks possible. But there's serious scholarly efforts where people review what he's done and say, you should have done this differently. The answers turn out a little different in this way, et cetera, et cetera. So for example, there's a paper by Cleveley and co-authors from Oxford who went very carefully through some of the things Romer has done and tried to correct some calculations. So I don't want you to walk away thinking that everything Romer does is great. Another thing is that, Romer has a Twitter feed in which he's, linking into, all sorts of new technologies that he perceives. And Romer is not advocating for RT-qPCR as we have been looking at it. He wants an unproven, not widely installed technology based on full DNA sequencing to be adopted. That will take much longer, in my view. Whereas RT-qPCR, as you can see, we're now up to testing, at the level where if we got a 10x improvement, we would be testing half as frequently as Romer wants. So we can get halfway to where he wants us to be just using pooling ideas. and the equipment exists and people know how to use it. So these ideas are relevant and so on. I want to point out there's a lot of work that I relied upon but couldn't review, that if you go to Chris Builder's webpage, so he's the professor at University of Nebraska, you can learn more about group testing as an idea. And there's a paper by Claudio Verdun and co-authors at TU Munich, which is again in the same group of medRXiv papers, but it's closer to the way data scientists think and you may like. I want to thank you so much for your attention. Talk materials are available at the tiny URL that's given above. And I think we have a Q&A coming up.
Thank you very much, David, for such a wonderful talk. There are a couple of questions and Geeta will be asking them.
Yeah, thank you from my side for a great talk. And already the questions are pooling in. So the first question was asked by Demba Ba, and the question is, in the Bernoulli sparse recovery setup for testing, are the regression parameters beta and the X vector of viral load both unknown?
Well, I mean, the machine calibration really gives you, so if you remember a plot that I showed that shows you as you go through thermocycles, let's see if I can get back to it, just a minute. I think it's this plot. So the betas have to do with the relationship between viral load and fluorescence. And what we're seeing here is that that relationship is quite rigid and quite clean and absolute across a range in the viral load of over 1 million. Because you're seeing essentially a rigid shift to the right every time we move down by a factor of 10 in viral load. That is essentially proof of the GLM's correctness. Now, you know, maybe offline we could pursue this more, but I'm just saying, you know, if you reflect on what this plot is showing, it's showing the correctness of what we're talking about. I hope that helps.
Thank you very much. So we have one more question by Toma Harari Haman. So he says, thanks for a very interesting talk. Since the pooling requires additional circles, are the costs of running the additional cycles and possibly fluorescencing negligible compared to the saving in testing kits?
Yeah, the cycles, that's an excellent point. So as you can see here, or maybe there was another plot I showed like this. That was a few slides later, I'm sorry. Yeah, okay. Here, so here's an unpooled sample, and you see that you're getting fluorescence above threshold at about 28 thermocycles. Whereas if you had diluted that, you maybe get, you know, emergence at 36 thermocycles. And so you have to do 8 more on a baseline of 28. So, you know, that's substantial. That's like a 25% increase in the running time before fluorescence is reached. But I think you have to go to 39 in order to meet the FDA EUA, so that routinely in a commercial establishment, they run it for 39 and they evaluate whether fluorescence is achieved by 39. So in the environment where there's a fixed number of 39 of cycles, you're not changing anything. You actually run every one of those cycles. It's just that the emergence comes, it's a little more, you know, towards the end, but it still happens before the end. But it does show you, I mean, it would be very hard to go to, say, dilution by a factor of 512 or something. You can see that that's a non-starter given the way these plots are going.
Thank you very much. So maybe as a final comment, Boubacar Ba mentions actually, and I think everybody can read it, a paper from AIMS Rwanda, also on group testing, and also that Rwanda apparently might be ahead of the FDA in approving pool testing. So he posts some references there. So now I think for the sake of time, I would now hand over to René for the final word.
Yes, I had a quick question before closing. So the methodology that you describe applies to one test, but you could be in a situation where you've got many companies that are developing different RT-PCR tests, perhaps with different accuracy, or you could be thinking about integrating different type of tests for example, the RT-PCR and antibody testing. So how would the methodology extend to those situations?
Well, okay, so as a research matter, I think particularly in the antibody testing situation, that's really a vital question. So the story of antibody testing is completely different than active virus testing, and it's because it's about everybody's antibodies are different. Every human who cooks up an immune response is doing it unaided on their own and inventing their own way to cope. And so there might be some consensus antibodies that many people have, but they're definitely, you know, individuals who discover Darwinianly inside their blood, they discover a really powerful neutralizing antibody with a very high attachment affinity. And then there'll be maybe other people, often older people, whose bodies won't discover very effective antibodies and so on. So you're testing for a very polyvalent situation, and you might need to test for lots of different types of antibodies in order to actually fuse those together to really understand if this person has been previously infected. Another thing in the RT-qPCR, there is a problem of a false positive which occurs like this. It's possible for you, like you were sick, you've gotten better, but if you do a test for active virus, it says you still have active virus even though you don't. And what's happening there is that the virus has been inactivated. However, the thing that inactivated it is not the sequence that's being tested for in the Charité hospital reference standard. And the only way to know that this person is not harboring an active infection is to actually look at other parts of the sequence and check if they're present. So, you know, some sort of multi-sensor fusion, to use the EE language, is definitely called for in this setting. Like if we truly want to understand the patient's situation, in a crisis, you know, we'll be very lucky. Just, you know, there will be a day, I guess, when we will have tested essentially everyone in the U.S. population. Like it's like a major triumph of science and technology and testing organizations and so on. I find it very challenging for us to do more than that. So I wish we had better testing and tests that fused multiple modalities of information. I don't see it a commercial option happening right now.
Thank you. Thank you very much, David, for such a great and illuminating talk. Thank you, everybody, for attending the SIAM Mathematics of Data Science plenary lecture. And I invite everybody again tomorrow at 1 p.m. for another plenary lecture by Jan LeCun. Have a great day.